Hi all, welcome to the second video of the Mechanics of Fluids video lecture series. In the last video, we have discussed about some basic concepts which are required for the easy comprehension of the subject Mechanics of Fluids. We have discussed about the definition of fluid and we have distinguished between different states of matters. We have compared solids, liquids and gases together, and we have discussed about the compressibility of a fluid, and we have listed two types of fluids. First one was incompressible fluid, which was considered to be liquid. Second one, compressible fluids, and we have seen that gases are generally considered to be compressible for practical purpose. Okay, and we have also seen the difference between a fluid and a solid, and how we will distinguish between a solid and a liquid. And we have stopped in this slide in the last class. We have compared solid, liquid and gases together with the help of some statements. These are the statements. The arrangement of atoms in different phases are explained in these three statements. Let us see. Molecules are a relatively fixed position in a solid. We can see from the diagram that here the molecules are closely packed and they are fixed in their relative fixed positions. And we can see there are certain bonds between the molecules so that they will be closely packed together. And also in the given volume, the number of molecules in the case of a solid is very large when compared to the other states of matter. Now, groups of molecules move about each other in liquid phase. In liquids, we cannot see the bonding like in the case of solid, so that liquid molecules are free to move about each other. But we can see that the number of molecules in the case of liquid is less than the number of molecules in the case of solid. So the given number of molecules within the volume, within the given volume in the case of liquid is less than solid. Now, looking into the case of gas, we can see that the molecules move about at random in gas phase. We can also see that the gaps between the molecules are larger than in the case of liquid. So here, gases are not only free to move in the confined space, gas molecules can move in a random manner, but also the distance between two gas molecules is comparatively larger in the case of gas when compared to a liquid and solid. Now, moving to an important concept called continuum. See, we have already studied the subject engineering mechanics. In that subject also, we have considered the matter as continuum, but it wasn't specified at the beginning of that subject. But here, since we are dealing with a core course, we need to consider this concept before going into the in-depth details of the subject. So, what is a continuum? Let us see. Fluids, like other substances, are made up of molecules which are always in motion corresponding to a given temperature. This statement means that when we are taking any state of matter, whether it be solid, liquid, or gas, all the matter is made up of microscopic materials, structural elements like atoms or molecules. But in our previous studies, we haven't considered, for example, in the case of engineering mechanics, we haven't considered the structural arrangement and molecular theory like that. We didn't consider those studies. We considered our matter, our material, like a continuous subject without even considering its molecule, atom, all those things. So in here also, in the case of fluid also, it is made up of atoms and molecules which are always in motion corresponding to a given temperature. But in most engineering problems, in the case of which deals with the fluids, the behavior of the individual particles in a system is of little importance. Why? We are not considering the behavior of the individual particles in most engineering problems, because if you are considering the individual particle behavior, like the behavior of the atoms, molecules and their motion, the solution will be very complex and the resources required to solve the problems will be very large. So it will be very tedious and time consuming. when we are we are solving the problems, engineering problems. So we need to somehow simplify the situation by using this concept, continuum, whereas we will not consider the behavior of the individual molecules. For example, we will not consider the behavior of atoms or molecules when we are considering our problem in continuum approach. That is the main difference. So the study of the motion of the fluid is made by treating the fluid as a continuum. The assumption of the continuum is that instead of dealing with instantaneous states of innumerable molecules like atoms or molecules, we will deal with certain macroscopic properties describing the gross behavior of the subject, also of the substance. Okay, this itself defines the continuum concept. Instead of dealing with instantaneous states of innumerable molecules, that means our structural particles. Instead of dealing with structural particles, we will consider the fluid as a continuum, which deal with certain macroscopic properties, which describes the gross behavior of the subject. I will explain this thing with the help of an example. Let us take an example like this. Consider a container filled with oxygen at atmospheric conditions. We all know that oxygen is a gas, which is basically a fluid. Now, oxygen gas is filled inside a container. Now, certain values will be specified here. This is only for the sake of example. You students don't need to memorize these values in exam point of view. This is only for the sake of example. For example, you need to explain about this as a conclusion only. Okay, no need of the values are required. So the diameter of the oxygen molecule is about 3 into 10 raised to minus 10 meter, and its mass is 5.3 into 10 raised to minus 26 kilogram. And the mean free path of oxygen at 1 atmospheric pressure and 20 degrees Celsius, that is atmospheric condition, and the mean free path value is 6.3 into 10 raised to minus 8 meter. Now, what is mean free path? This can be explained with the help of a diagram. Let's see this diagram. Here, a volume is considered, and in that particular volume, we have 3 oxygen molecules. We can see the gap between the molecules in the case of a gas. We have already discussed about this. The gap will be larger in the case of a gas. So in this case also, there is a considerable void or gap between oxygen molecules. So here 3 oxygen molecules are shown. Consider a single molecule among this. We are considering this molecule. Now we will consider the collision of this molecule with other molecules. So this molecule will travel to this molecule and it will collide with this molecule. So immediately after the first collision of this molecule with this molecule, we will measure the distance. So after this first collision, suppose this molecule is moving towards the next molecule, the third molecule, and we are somehow measuring the distance from the first collision to the second collision. That means after the first collision, this molecule will again move to this molecule and it will collide with this. So the distance between these consecutive collisions are somehow measured. And if you are taking all the distance between 2 consecutive collisions in the system, similarly in this case of a molecule, there will be another innumerable molecules in this in this condition. So if you are taking all the path or the distance between 2 consecutive collisions, and if you are finding the average value of this distance, that average value is called mean free path. Okay, so that value will be considered as constant value. So in the case of oxygen, the mean free path between 2 consecutive collisions will be 6.3 into 10 raised to minus 8. Now let us compare this value with the oxygen molecule diameter. So after comparing this oxygen molecule diameter, we can see that the oxygen molecule travels on average. That means its mean free path is 6.3 into 10 raised to minus 8 meter, and it is 200 times its diameter. That value, this distance value between 2 consecutive collisions, it is 200 times its diameter before it collides with another molecule. That means the gap itself is very large. The distance between 2 molecules before collision will be very large when compared to the diameter. That itself explains the large void, the presence of large void or gap between the gas molecules. Uh, and there are about 2.5 into 10 raised to 16 molecules of oxygen in tiny volume of 1 millimeter cube at one pressure, 1 atmospheric pressure and 220 degrees Celsius. Even though there is a large void or a large gap, by considering the number of the molecules, we can see there is a large number of molecules within a tiny volume. We can consider, even though there is a presence of this large void or gap, we can consider this situation as a continuous object. We will assume that this volume is completely filled with oxygen, considering this large number of molecules of oxygen, even though there is a gap. This condition is called continuum concept. This approach is called continuum concept. So, despite large gaps between the molecules, a substance can be treated as a continuum because of the very large number of the molecules, even in an extremely small volume. Okay, so this example well explains the concept behind continuum approach. Now, this approach, we will consider this approach throughout our fluid mechanics, and also the subject you are studying along with this subject, fluid mechanics. The subject is called Mechanics of Solids, MOS. In that subject also, we are following this concept. In there also, we will not consider atoms or molecular structure of the subject of the material. We will consider the material as a continuum, as a continuous material, and we will apply the same concept in that subject also. But in certain subjects like material science and metallurgy and all those subjects, we will consider in certain portions, we have to consider the atom or molecular structure of the material. So in that case, only we will go to the details of that structural anatomy of the material. So in some conditions, we need to come out of this approach from continuum approach. So certain subjects at certain topics we need to go out of this continuum concept. But throughout this subject in mechanics of fluids, we will be continuously following this continuum concept. And what if we cannot apply continuum concept? In certain conditions, we need to consider this atom or molecules. In that condition, we will leave continuum concept, and all those equations from the continuum concept we cannot use that. Instead of continuum concept, in that case, we will consider molecular dynamics. That is entirely different area, and that subject will be studied in the higher education. It will not be studied in BTech course. You can study that subject in your post graduation or like that. So that is mainly considered to be a research topic, molecular dynamics. In that area only, we will consider the atom or molecular structure in fluid flow and gas flow, etc. Okay. So from now on, we will be explaining fluid mechanics topics purely on the basics of this basis of this continuum approach. So that's all about continuum approach or continuum concept. From next class onwards, we will start our main topic, properties of fluids. Thank you.